Thank you again. Yes. So here we are. We're recording again. Haven't gotten too far along, so you didn't miss too much. Uh, and so we have all this data. We have this enormous amount of data. And are the statistical tools that I am teaching you and that you learn in your books, are they good enough? Are they good enough to do this? Because, look at this. We got 28,000 train departures every day that we are collecting, that, well, not we, not me, but Spain and Denmark is collecting. And if I'm going to do a statistical test on 28,000 values, is it going to work? And unfortunately, the answer might be no, it's not going to work. And let me show you why. Let me get my mouse to click here. So why can't we just push the button, right? Why can't we just throw this into the software and push the button and get an answer? And so I'm going to mention two examples. I'm going to give you examples about distribution fitting. And I'm also going to talk about what happens when, in fact, the distribution you're trying to fit is not really one of the standard textbook distributions. So let's do a little experiment here. So I went into SAS and wrote some code and said, generate 100,000 simulated values from an exponential distribution. Just do it. There's 100,000 values, exponential distribution with a mean of 1. Just went in and did that. And now I created this data. I know exactly what the source is. This is just like the lecture I gave you like 4 weeks ago, right? I created some data in Excel, and then I created the confidence intervals from that data, and then I showed it in Excel. So I'm going to do it again here, but in SAS. So so I create this data, and then I just run the very basic SAS test on this data. What are the basic statistics? What distribution does it fit? You can just, this is really easy in SAS. There's even a graphical version. You just do this. And so it says, yep, thank you. It's exponential. Thank you very much for participating. Here is your result. And the statistics and the tests tell me that this is exponential. Great. And this table over here on the right, these 3 tests, I have not taught you this. I don't know if you've ever seen these before, but these are 3 tests for checking. These are more advanced and fancier and better than the little chi-square goodness of fit test we showed you in this class in the lecture slides. But these tests you can't just do on your calculator. These tests are more difficult, so you need software to do them. You can't just do them by hand. Anyway, and the answer for all 3 of these is a larger number is better. So the p-value should be large. You want a large p-value. So these are all good. They all pass. Fine. So now let's talk about the real world. That data was artificially generated from SAS, direct from a distribution. In the real world, the data is never so clean and neat. In the real world, there's errors in the data collection. In the real world, there's stuff that goes wrong. And I've mentioned this to you guys before in some of our lectures. In the real world, there are mixtures in the product flow where maybe it's not all the same stuff you're measuring. So what happens to that when you add that into your sample? So we look at this. So what I did is I took that data that I just generated to pass the test, and I add some noise to it. I purposely disturb the data. So I add a little normal distribution error to this data at a 1% level and at a 5% level. And then I round the, and then not but I mean also I have a 1% error and a 5% error. And then a third way I disturb the data without the error, not including the normal distributed error. A third way I disturb the data is I round it. I round the data. And this is actually really important. You know why this is really important? You know why this started? Because Spain Denmark rounds the data. So all the data that we got from Spain Denmark on their train schedules is rounded to 10 seconds. So all of the delay data is rounded data. So already, this is a problem because we have already now disturbed the data and violated the very principles of all these goodness of fit tests because the data is rounded. So that was what motivated this entire research. But anyway, here are the results. Here are the results. So now what I've done is I've sampled this data 5 times. So before the first slide, I said it took 100,000 values. So each one of these columns is a brand new 100,000 value sample in SAS from the exponential 1 distribution. So the very first row up here, that is the original picture, the first slide I showed you, and they all pass, right? This is all p-value greater than 0.05, and they all pass. Some of them pass crazy strong. This one is a little bit weak, but it passes. So that's 100,000. But then I add that error. I add that normally distributed error I told you about. I add that 1% normally distributed error, and none of them pass. None of them pass. So what does that look like, 1% error? Actually, maybe I should make a picture of that next time because I don't have a picture of that in this presentation. You've got the exponential curve, and then 1% is just going to be like a little bit of static on that curve like this. Like it's just going to be kind of jiggling a little bit as the line. It's just the shape is still there. The shape is still there. We just have a little bit of a jiggle, just a little bit of a jiggle, and it's centered on 0. It's a 1% error centered on 0. So for all the points that fall below the line in error, there's going to be an equal number of points that fall above the line in error. So it's a cloud of disturbances going along. So the shape is still there. The data is in fact really not changed, but none of them pass. None of them pass in using the standard test tools in SAS. And then I reduce the sample size. So let's go to 50,000 values. And we still don't pass. But then I drop to 10,000 values. So this is the same distribution and the same error function. And I drop the sample size to 10,000 values, and they all pass. They all pass. And then I drop it to 1,000 values, and they all pass. And then I go to the high error, the 5% error at 1,000 values. And a bunch of them pass except for 2 out of 5 do not pass. And then I drop the sample really small to 125. And of course, they all pass. So this is the problem, and that I could have completely accurate data that is completely, reasonably error-free, that is completely accurate for a very specific distribution. But just because I have a really large amount of data, my tools don't work. The statistical tests don't work. That's a problem, right? Because you want to collect your Bane of Denmark, you want to collect all this data, set up some kind of computer, and just keep processing it. But if the answer is going to be the more data you collect, the worse your results are going to be, that's not so good. So what do we do? What do we do to fix this? Let me show you what we do. And here's the rounded data. So this is the Bane of Denmark rounded data. And again here, with a 5-4 rounding, where you round up at 5 and round down at 4, we're not too bad. A lot of the tests pass. But with the round up, which is what Bane of Denmark does, Bane of Denmark is a round up. It's a round up to 10 seconds. They all fail. They all fail. So what are we going to do? Here's another potential problem. A mix of 2 processes. This happens a lot. This happens a lot in business and processes. You have 2 assembly lines for the identical product, but they're going to generate different results because the employees on one assembly line work differently than the employees on the other assembly line. So even though they're the same product, they're not the same product because different people behave differently. So they generate different flows and different percentages or something like that. Or for example, on the Kystbane, we can start talking about comparing Urson's toe to the other trains that run Helsingør direct to Roskilde. You know, there are different processes. They're different equipment, different crews, different driver. So that's another possibility there. So anyway, let's imagine this two process. We have two processes, one with an exponential 1 distribution and one with an exponential 2 distribution. And at the end, the product comes out and just gets dropped in a big bucket and it's all the same. And then we measure from this bucket. So this is a mixed distribution. So what is a mixed distribution? So on the left, we have two separate normal distributions. Imagine what happens if you take those two separate normal distributions and you just throw them together. You sample from both distributions, and the results, you just throw them all together in a big pile, in a bucket. The one on the right is what the sum of those two distributions looks like. So it's a little different shape. In this particular case, it's fatter. It's a little bit fatter. So I don't go through all the results here because this presentation is meant to be kept to a certain short length. So I do the same kind of test that I did for the previous data set, and the results are the same. 100,000 values, mixing these two distributions, nothing passed any of the tests. Nothing is valid. But if I just cut back, if I just make the sample smaller, if I just make the sample 250 data points, suddenly it passes. Suddenly it's good. And SAS says, yeah, this is an exponential distribution with a mean of 1.5, because it's, of course, the mix of a 1 and a 2 exponential distribution. So it passes with a small sample size, and I have a significance, I have a p-value of 0.056. So it passes at a 5% significance level. So this is a bit of a tricky problem. How do we deal with this? Well, there are a couple of things we could do. One is to look at the data graphically more intensively and look for visual symbols that this data is not what we think it is. In this case of the two mixed exponentials, there's a whole research area in telephone switchboard theory. And in that theory, they've discovered that a lot of really great results can happen if you transform the data to a log base 10, and when we talk about transforming, that's something we will do in this class next week in trying to solve some of our linear regression problems. We will start transforming data next week. But for now, if you've never heard of this before, you just, okay, it's fine. Just let it go. So we transform the data, and then that data transformed then fits what is called a mixed normal distribution. And that can be done, for example, in R automatically with software. And then we have to test it. And the tests that I've given you and the tests that are standard will not work for this, because they are the ultimate answer is the tests that are typically taught, the tests I gave you, such as the chi-square goodness of fit and the Kolmogorov-Smirnov and the Anderson-Darling and all these other tests, they are really sensitive to sample size. What happens is, as the sample size gets really large, they become hypersensitive. And they become so sensitive that the littlest little bump in the data just sets them off crazy. So we need a different kind of test. And this is one really good example of an alternative test. It's called the Mann-Whitney test. And these two gentlemen are Mann and Whitney here in the pictures. And it is a test, and it does appear in your textbook. It gets about a page and a half of description in your textbook, but it is a test that you can use much better in situations where you don't want so sensitive a test. You want a test that is better at looking at the shape and not so much at the details. You want more of a shape sensing test. And you can get this test in R and in SAS. So how do we do this? This is the testing procedure right here. So you have your data, and then you run it through SAS without any changes, and you just do a quick check to see if SAS accepts it as it is. And if it does, if SAS accepts it or R accepts it, then you say, okay, maybe we'll just go with that. But if it doesn't accept it, or if you have doubt, if you are not sure about whether this is really the correct way to go, then you artificially create data from a distribution that you think is the right fit to this data. You generate it artificially, like we have done in Excel, or like I did in SAS. And then you take the observed data from your original data, and you take these generated fake or synthetic values from the suggested distribution, and you put them into the Mann-Whitney test. And the Mann-Whitney test does a test kind of like the chi-square goodness of fit, but it's got a whole different set of formulas that I'm not going to go into. I'm not going to go into details. And it is much more likely to come out and prove or demonstrate an agreement between these two data sets, and then give you evidence that they are in fact from the same distribution. So here's the case study. Here's the case study for this presentation. This is what motivated this entire conversation. So we were looking at the Kystbane, and we had the data from Bane of Denmark, and we have the data from 11 stations along the Kystbane, everything north of Oosterpoort. It was basically north from Oosterpoort to Helsingør. So the 11 stations north of Oosterpoort. And it was like 3 months worth of data. I think it's 3 months worth of data. And in that data, we have 75,000 individual departures, individual time-stamped departures from stations. And some of those departures are early. There is actually quite a lot. A lot of trains leave early. Maybe you already knew that, but a lot of trains leave early on the Kystbane, especially at intermediate stations. So out of that data, if we take out only the late departures, so the 55,000 late departures that are non-zero, that are non-negative, positive delays, zero or positive delays. And then we want to model this. We want to see what the data is. So what did we do? So, and why are we doing this? Why do we care? Who cares? Who cares? Why are we doing this? Because for one, because of the DSB travel guarantee. So DSB has a travel guarantee, and that travel guarantee has a financial liability. So when DSB makes this guarantee, they need to plan in advance a budget for this guarantee. There needs to be money set aside to pay this. How do you figure out what that budget is? How do you figure out how many million kroner you got to set aside in a bank account to pay these claims on this service guarantee? Well, you got to do this. You got to collect data, and then you got to generate a distribution for the error term, or for the delays, and then you got to use a forecast from that distribution to figure out what your future delay is going to be. At least you should be doing that. Maybe they're not. Maybe they just like, well, I don't know. We'll just like make up a number and put the money aside. And if we don't have enough money, the government will pay for it. I don't know. I actually have not posed that question to them, but this is what they should be doing. Anyway, so here's what we got as a result. Here's what we got as a result. We just throw the 55,000 data points into SAS, run Proc Univariate, Computer says no. Computer says, nope, doesn't work. I can't get it to fit. Doesn't look right. This is the normal, this interior plot here with the funny line and this tailing off here. That's called the normal probability plot. It's a disaster. It's a complete disaster. But the funny thing is, all of the research, if you read all of the published research, many of those papers coming from authors in the Netherlands and Sweden, if you read the published research on train delays, most of them will tell you that the train delays are exponential. Most of them will say that. Most of them will say, yep, this is an exponential distribution. Problem is, all of their sample sizes are like under 200. All of their sample sizes are really small. And so what are we going to do here? We got to find out what the real distribution is for this thing. We need to know. This is important. And I'll show you why it's important here at the very end. Let's take a look. So first little lesson here. Don't just rely on the computer. Don't be so dumb that you just throw the numbers in the computer and look for the result and say, I'm done. I'm going home. See ya. Time to get the kids. No. What is the theory of the distribution you're trying to fit? Does it match the behavior of the data that you have? So an important behavior of the exponential distribution is it is memoryless. It is memoryless. And it's kind of hard to explain, but it basically means that the exponential distribution does not change its behavior as you roll forward in the data process. The forward vision of the exponential distribution never changes. Let me give you an example. You're driving your car and you're looking out the windshield and you see the road and the road is going up the mountain. Imagine you're in your car driving and you look out the windshield at the road, and that view of the road never changes. No matter how far along the road you drive, no matter what the road looks like behind you, the road in front of you out your windshield never changes. That is the memoryless function of the exponential distribution. And so here in this graph, the blue line is what I expect the behavior of this data to be if it were memoryless. But in fact, it's not. And the Kystbane data has a very clear change in behavior as you look out that windshield and look forward as the car is driving. And we also expect in an exponential distribution that the mean and the standard deviation are equal, and that's also not true for this data set. So there's a lot of suspicion here that this is in fact not an exponential distribution. So to cut the presentation short, because this is a timed presentation for this conference and I keep the information short, we're almost done here. To cut it short, what happens is this is in fact a mixed distribution. It is a mixed distribution containing two separate exponential distributions. And what this picture is showing right here, this picture is this is the data scale here is transformed on a log base 10. So we take the data and we transform it log base 10, and then this, if we do that, then the distribution of the data is some kind of mixture of normal distributions. So what this is a mixture. This first red line is one exponential distribution that's been converted, that's been transformed log base 10 to a normal distribution. And then this second red line is another exponential distribution that's been transformed base 10 into a normal distribution. And the two of them together create this green line. This is the mix of these two distributions. And this blue line here is the histogram of the data transformed log base 10. So you can see the green line is a really strong match to this blue histogram of the transformed log 10 data. And so this long formula here is the exact, and there was another part where we added a max function and clipped the data, and I explained, that's explained in a paper we wrote. But anyway, it's basically a mix of two normal distributions with very complicated looking parameters. And that function, we run that through a Mann-Whitney test, like I showed you on the previous slides. And that function gets a p-value of 0.6. So it's a complete win in terms of arguing from this data that we have found a good mix, good distribution to this data. So we're almost done here, and there's only one thing more to show, and that is I motivated this. I told you at the beginning, the whole point of doing this was because we need to figure out what our liability is for this ticket guarantee. What is our financial liability for this delay? Well, if I had accepted the published statements that this is an exponential distribution and maybe had only sampled, 500 data points or something, and then built a distribution based on that, the left side is an exponential distribution with a mean of 2.5, which matches the statistical mean of the data that I collected. And on that figure for that exponential distribution, I have colored in where the 3-minute measurement point for delays on the railways happens. So in Denmark, 3 minutes is our trigger point. 3 minutes and the train's late. So anything in the blue is a late train. So 30% of the trips, 30% of the data points under this distribution trigger that delay. On the right here, this is a cumulative distribution drawing of this mixed distribution I showed you in the previous slide. I did this in Mathematica. I coded this in Mathematica and then generated the chart and all this stuff. And then here and it's a log 10 scale. So, you gotta, but on this log 10 scale, this dotted line and intersection, this is the 3-minute point on this log 10 scale right there. And when I read that scale, I've got about a 22%. I have a 22% trigger of delay. So that's a pretty big difference when we're talking about millions of kroner. We're talking about thousands of passengers, millions of kroner, and the expense of transacting all of those compensations, all of those payments. 30% and 22%, that is basically, depending on how you want to measure it, that's basically 25% less under this distribution than under this distribution. So if we were budgeting for the expense of paying out these claims, my distribution would mean a budget that is 25% less than this distribution on the left if we assumed it's just exponential. So there's a huge potential cash difference in the budgeting and in the financial liability, depending on which of these two distributions you really believe are correct for these delays. So that's the presentation. And I think it's a little advanced for our course, and it covers a lot of stuff that, we probably, I don't know, if we're lucky, it won't fit because we're going to be spending all our time on linear regression and a whole bunch of other stuff related to linear regression. But it's kind of a point to bring up to say, hey, what is the real world? What do I need to do to actually have value from all this statistical knowledge? And what are some real world applications where I might actually be doing something? And what is the possibility that I get it wrong, or that, it's not so simple to just pull out the Excel spreadsheet and run some things, or maybe just run Proc Univariate on SAS. But maybe you need to have a little deeper insight in what's going on. And so I thought this would be nice to share with you, and a relatively short presentation. So that's it for today, folks. Any questions on this presentation or anything else? And then I'll say goodbye, and thank you for Ken. Thank you very much for your praise. But it just shows you, you start out with a little thing, You're like, oh, we just learned a couple of statistical things. And then somebody is like, oh, wait a minute, there's a whole lot of stuff here that we got to worry about. But the positive, I mean, the rewarding thing, the reward of doing all this is coming to a point where we can say, hey, I can actually turn this into some financial meaning. This actually has value. I can, I might actually do something that makes a difference at the operation of some transport firm or something. And to get that operational difference, you do need to keep your eyes open, think about the theoretical implications of what you're doing, and try to keep your head in the game. Try a couple of different situations and compare the results and see what happens. So that's it, I think, for this. I think that's the end of this show. And thank you very much. And I will get all these little small questions you had about exam. Figure this stuff out. We'll get it out. But I'm overall, I think the exam went well. I think, again, like I said, when I can look at an exam and a large number of people get, a large number of questions, everybody has it correct. That is great, because I'd much rather have everybody get one question wrong than have random people getting different questions wrong through the whole exam. I think it's just better. I think so. I think most people are on track and know what they're doing, and from this exam have a better perception of what we need to focus on to stay on track going through the rest of the semester. So I'm going to call it quits here and say goodbye. I'm going to stop the share and I'm going to stop the recording.